regression that we call beta regression. Okay. Now, just like what I said the other time, what determines the regression type to use is the nature of the response variable. I'm going to say that again. What determines the kind of regression type to use depend on the nature of the random variable. When the random variable is continuous and it's not bounded, we're actually going to use, we're going to specify linear regression for that. But what if in a situation whereby the response variable is categorical? Categorical in the sense that we got two levels. Of course, we're going to make use of binary logistic regression. But what if in a situation whereby the response variable or under investigation is neither continuous nor categorical, but is a count? Then we're going to use a Poisson regression. But what is new today? Okay, today we want to focus on a random variable that is continuous, but is bounded between 0 and 1. I'm going to say that again. It's continuous, but bounded between 0 and 1. Then what type of regression we're going to use in that situation? We're actually going to use a beta regression. So I welcome you to beta regression, because in the outline, I'm going to talk about a quick review on logistic and its variant, which I've just talked about, then going into beta regression without wasting my time. Without wasting my time, I'm going to first give you an example of a random variable, a response variable that requires the use of a beta regression. It means that that particular random variable on its own can be, follow a beta distribution. In statistical theory, we have what we call a beta distribution. Okay, a beta distribution is a probability distribution. It's a continuous probability distribution for a random variable that have a state space bounded in the region of 0, 1. An example could be proportion. When you're talking about proportion lies in the interval 0, 1. What about rates? What about percentages? Okay, all lies in the region 0, 1. And a very good example of that, if I want to talk about, maybe you should tell me what is the percentage of time in a day that you spend studying. That actually varies. That is going to be in interval 0, 1. If I want to look at the relationship with that and some other variable, then I should be thinking of specifying beta regression. What about vaccination rate? It is not everybody that will be vaccinated. 100% of people cannot be vaccinated. If the government want to know the awareness campaign, they really want to see whether they've been able to bring a lot of people on board. If you really want to investigate intervention, of course, beta distribution or beta regression model will enable us to identify some variables that have connection to being vaccinated. So vaccination rate, okay, can also be modeled using beta regression because the response variable actually going to fall between 0, 1. Okay, what about defective rate in a company? The numbers of defective, it is not all the product that you produce that will be defective. You want to figure out how many of them that are defective. They'll talk about proportion. What about the proportion of income that you spend on food? It is not all your income that you spend on food. What about poverty rate or poverty rate and so on like that? So there are so many applications in this area. Now I welcome you to beta regression module. Now, what I'm trying to show you now, for you to be able to understand the underlying distribution for a response variable that are continuous and are in the range of 0 to 1 is what we call a beta distribution. The underlying distribution for linear regression is normal distribution. The underlying distribution for logistic regression is binomial distribution. The underlying distribution for Poisson regression is Poisson distribution. The underlying distribution for beta regression now is a beta distribution. In statistical theory, we got a beta distribution. We actually use a beta distribution to model a random variable, that is in the boundary of 0 to 1. And what I'm trying to display right now is it has a lot of flexibility, okay, because a beta distribution has two shapes parameters. If I really want to know how flexible is a model, that depends on the number of shape parameters the models have, okay. And let me tell you this, we don't want a situation whereby our model is going to be rigid. A rigid model is not fine, because what happened in reality to commiserate with the model we're going to apply, because in reality things are changing, then we need a versatile model. We need a model that is dynamic. We need a model that's actually going to change. Or the way reality change, the model also going to change. And that is the reason why we need a good number of shape parameters in the model. In a beta distribution, we got two shape parameters, and that account for its flexibility. When a model is flexible, the model will be versatile. Okay. Now, this is just to show you the distribution. Okay. This was statistical theory, having an understanding of the underlying distribution of the response variable. Don't forget, the response variable here is what we're talking about. Okay. Now we've now started talking about explanatory variable. What really determines regression type to use is the nature of the response variable. And that is why right now, okay, we believe if y is in the region of 0 to 1, the distribution is beta. That is the beta distribution, and that's exactly what I'm trying to show you right now. But you know what? If I want to go from this to modeling, then I need to reparameterize as given by Ferrari and Cribari Nero 2004. Let me tell you this. When I have a beta distribution, the mean of a random variable following a beta distribution is that P over P plus Q. We can use alpha over alpha plus beta. Here, I'm just trying to say P and Q represent the shape parameters that we're talking about. So the average is that. But you know what I'm going to do? If I let phi to be P plus Q, wherever I see P plus Q in that function, I'm actually plugging in phi. And wherever I see P over P plus Q, I'm going to plug in mu. Because in modeling, there's a difference between a model with covariate and model without covariate. You know what? The first one, a distribution, is a model without covariate. Do you see anything covariate? Do you see explanatory variable? It's just y. It's just the response variable. That's what we mean. Model without covariate. Model without covariate, we're referring to the distribution, the underlying distribution. Now, if I now want it to have a model, a parameter associated with the one with covariate, if I let mu to be P over P plus Q and phi to be that, plugging that in, what do I have now? I'm no longer having P and Q anymore. But what I'm having now, I'm having phi and mu. Why? What is the essence of the mu? The mean is the model, the average in the model, like expected value of y given s. Okay. Now take a look at this. For you to understand what I mean, I said according to the distribution, expected value of y equal to that, which is the mu, and this is the variance of the distribution. We're focusing on the distribution now, beta distribution. Now, going into beta regression model, okay, what we now want to do is we are now focusing on mu and phi. Okay, what is mu? Mu is the mean. What is a phi? Phi is a precision parameter. We move from a beta, we want to move from a beta distribution to a beta regression model. A beta distribution is a model without covariates, but a beta regression model is the one that accommodates covariate. Therefore, the parameters in the beta distribution need to be remodified to accommodate the mean and precision parameter. That's exactly what we mean. Because of that, now we can rewrite that y follow beta now with new parameter mu and phi. And you know what? Expected value of y equal to mu. The variance of y is going to be that in terms of mu and pi. Now, what the dispersion, from the precision parameter, take a look at this. Some of you may be wondering, what is the essence of phi and the mu? Of course, the average. If a response variable, if a vaccination rate lie between 0 and 1, for example, please pay attention. If vaccination rates lie between 0 and 1, then the mean of the vaccination rate also going to lie between 0 and 1. That's what I mean by mu lie between 0 and 1. That mu could be average poverty rate, could be average time you committed to study in a day. Does that make sense? Okay, now what about phi? Phi is a precision parameter. That is, how precise is my model? That's what we call phi. And you know what? What is the inverse of phi? If I want to consider 1 over phi. Oh my God. 1 over phi is going to give us the expansion parameter. The expansion parameter. When phi is large, the expansion is going to be small, right? So phi is a precision. When precision is large, what happened to the expansion? Small. When the expansion is large, what happened to precision? Is not going to be fine. And that is why, don't forget, we cherish two things in the model. We want to look at the average relationship between the response and the explanatory variable. We also want to look at the precision. How precise is the relationship? And that is the reason why this is parameterized. Now you know what I want to do now. When y1, y2 up to yn is a random sample, okay, from a beta distribution, then what we're trying to say, we can apply a beta regression model. This is going to be the beta regression model. What you are seeing here is in a matrix form. Do you now see that I've introduced what? X, that X transpose. That X may be X1, X2. Maybe, for instance, I really want to know what affects vaccination rate. Maybe the government want to know what affects vaccination rate. And they now go to the literature, or they ask people, they identify some explanatory variable, X1, X2, up to Xn. This is what we're talking about. Okay. And of course, we're going to have so many regression parameters, right? Beta 1 to beta k, depending on the number of explanatory variables. Does that make sense? Okay. Now, this is what I'm going to save you time from rigorous mathematics. If you take a look at what we're doing here, if this is the variance of vaccination rates, when I say vaccination rate varies from time to time. Poverty rate varies from time to time. Anything that varies from time to time can be regarded as a random variable. Now, if it is a random variable, what is going to exist? There's going to be the mean. There's going to be variance. This is the variance of yi in terms of mean and the precision parameter. Does that make sense? If I now want to incorporate the model, wherever I see mu, I'm going to be plugging in this. If you take a look at what I've done here, you're going to see. Don't forget, let me take you back. What do we define as the mu? Do you see the model is always the, when you take a look at when you take a look at this guy. Okay, now S transpose beta, right? Now that is actually going to be the mean without the error, right? If there's no error, you're talking about the mean because the expected value of the error equal. Now what I'm trying to say, mu I is this guy. Okay, mu I, that's what I'm plugging in. Do you see that? I'm plugging, what am I plugging into the mu now? I'm plugging the linear combination of the explanatory variables and their regression coefficient. Maybe something, maybe variables we have identified that affect poverty rates. If you are working on poverty rates, does that make sense? And the approach that we use here, if you take a look at what we're doing in 2, okay, the approach that we use here is what we call the likelihood function, okay? But you know what? I'm going to save this. It's actually maybe beyond this class, but just trying to tell you the approach that we use. What we program here is this. What we program here, what we program here is the distribution, is this guy here. You know what we did here? For this, if I want to estimate parameter, I'm actually going to first take the natural log, okay? Then after taking the natural log of all of this, okay, I find the likelihood they take the natural log. That is exactly what you see, what we're doing here, okay? But this is just to tell you, for beta regression, we don't use ordinary least square to estimate parameter. We use the method of maximum likelihood. So, but you can save that for now. But let me quickly go into something for you. Now, let me go into an example. You will really understand when it comes to example. But take a look at this. We're interested in the variable of interest is yield, which is a proportion of crude oil converted to gasoline. Let me tell you this. It is not all crude oil that are converted to gasoline during fractional distillation. You know, American is a world largest producer of oil and gas. When they have, you know, the crude oil, okay, then we have to do distillation, purifying it, okay, before they convert. Now, you may be interested in the proportion of that, of crude oil that was converted to gasoline after distillation or fractionation. Okay, those in industrial chemistry really understand this. And of course, if I now want to link this to some explanatory variables, then I'm going to fit beta regression model because of the fact the nature of the response variable here, which is the proportion of crude oil that get converted to gasoline. That will be between 0 and 1. Okay. Now, you know what we want to do now? Now, like I said, the uses, the gasoline yield, the proportion of individual infected, maybe with a disease. It's not everybody that will be infected. Does that make sense? And if I really want to explain, what are the reasons why people are infected? Then I should use a beta regression model. Now, I want to walk you through how do we do beta regression in R. This I need you to pay attention. If you want to use a beta regression in R, you need to load a package, install a package that we call beta reg. Beta reg. You have to install that. When you install it, you're going to load it. When you load it, do you know that there are some data that come with R? If you load this, you can actually have access to data set on gasoline, the gasoline yield. Okay, this is going to give you, if you write that in out, the way you write package called beta reg, you're actually going to have data set that has to do with gasoline yield. Now, you know what I want to do? How do I perform a beta regression in R? Maybe we've already, the industrialists or the chemists has already identified some variables, some explanatory variables that have connection to the yield, to the gasoline yield, like what? Bash. Okay. They produce that in different batches, and they notice that the yield are not the same in different batches. And they also identify temperature. Okay. And what are we trying to do here? This, oh my God, this is a code. If I really want to run a beta regression in R, just like a similar code. But let me tell you, something. Do you see that beta reg? For the linear regression, you see LM, right? For Poisson regression and logistic regression, you see GLM. But for logistic regression, when you see GLM inside that, you're going to see family equal binomial, right? And for Poisson regression, you're also going to see GLM family equal Poisson. But right now, if you want to fit a beta regression model, okay, you're actually going to write that code, beta reg, after installing and loading the package. Then you have that. Let's see the summary. Let's see what is going to come out. Okay. Now you're going to have this result. Oh my God. Look at this result. What do you see again? This result is coming with a Z. Do you see this is Z value, right? And that is the reason why beta regression, Poisson regression model, they are all variant of logistic, because even in logistic, you're going to see that Z. They belong to the same family. And that's why we call them the variants of logistic regression. What can you see now? How many batches? Can somebody tell me, based on this result, how many batches do we have for extra credit? Or what about online? Somebody said 9. Some people said 9. Why? Why? Exactly. Send me a message for extra credit. Batch is categorical. And arrow is reporting 1 to 9. Okay. If arrow is reporting 1 to 9, then 1 has to be nested. 1 has to be referenced. So which means they are 10 in number initially. Does that make sense? Okay. And you can see temperature. That's a continuous. This is not categorical. Now, based on what you're seeing here, what can you say about the p-value? Significant, right? If you look at the Fed batch. Okay. But you know what? We can also have a way to improve. This is a conventional beta regression model. Researchers have done a great job improving on this model by considering the expansion. Take a look at this now. Okay, variable expansion model. Okay, now I'm going to tell you the meaning. Take a look at what I said. I said, although the beta model already incorporates naturally a certain pattern in the variances of the response. Now, please, I want to say something here. Please pay attention now. Why is it that we cannot use a linear regression for a data that is categorical, while we use logistic the other time? Because there's going to be a violation of assumption of using linear regression. Why in this study now, why is it that we cannot use linear regression as well? We cannot use linear regression because there's going to be a violation of constant variance. I'm going to say that again. The reason why we cannot use a linear regression for situation where the response variable is a rate, where the response variable lies between 0 and 1. Okay, it's continuous and bounded between 0 and 1 is because of the fact that there's going to be a violation of constant variance. So naturally, the beta regression model as a way to accommodate that violation, and that is why we're using it. You know why? Because beta regression is flexible. I told you the other time. Because of its flexibility, because of the shape parameters in it, okay, it can actually overcome, that violation. But you know what? I said that even with that, we can still improve more on our beta regression model, even though we know that a beta regression model has handled that violation. And that was why I said, although the beta module already incorporates naturally a certain pattern in the variances of the response, it might be necessary to incorporate further regressors to account for heteroscedasticity. What do we mean by heteroscedasticity? Heteroscedasticity means no constant variance. That's a violation. Variance is changing. That is the meaning of hetero. Does that make sense? Heteroscedasticity is a problem in statistics. Okay, that's a situation. Heteroscedasticity occurs when there's a violation of constant variance assumption. Does that make sense? Now, you know what we're trying to do here? When a problem occur in Y, you know what we want to do further now? Even though the beta regression has already taken care of that variation, but do you know it is also necessary to see whether any of the explanatory variable play a role in that violation. I'm going to say that again. You're actually going to improve on your beta regression model if you further consider the role played by an explanatory variable in the violation of the constant variance. And that was why I said it might be necessary to incorporate further regressor to account for the heteroscedasticity. Now, please pay attention now. My model is going to change. What have I done? Please pay attention. I'm looking at the effect of batch and temperature. And I believe maybe what causes that violation could be temperature. How do I know that? Because statisticians normally work with those who work in the other field. Maybe somebody that is doing this in the lab told us when they are looking at the effect of temperature and batch on the yield of gasoline yield, okay, what normally cause issue at times could be temperature you are using, because you are eating the raw material, you are like supplying a lot of it. Okay, now you know what I'm trying to do here. It means here I'm considering temperature as a dispersion variable. Now, how am I going to know whether it's considering an explanatory variable as a dispersion variable work? I need to look at the summary of the result. When I look at the summary of the result, I look at it's only going to give you the only of the one for the temperature. You're only going to see a p-value for the temperature only. And what is that? That is what significant. If you take a look at the p-value here. Now, what that significant means? It means that temperature as a dispersion variable has a significant contribution to the problem of the heteroscedasticity. Now, and that was why I said that signal a significant improvement by including that. How do I know a significant improvement? I look at the p-value. Now, but somebody can argue this further. Okay, we know that is significant now. But can we have a way to compare the first model, which is this model? If you take a look at this model, if you look at this model, we are not considering any variable as a dispersion variable. This is just the conventional beta regression model. And also I call dy logit, the second one 2. Okay, but so the second one 2. Okay, if I really want to know, we can have a way to compare the two models at the same time. Just like the way we do it in nested regression model, where I remember when we were working on the linear regression model, where we use ANOVA into the simple model, comma complicated model. In this case, the conventional beta regression is going to be a simple model. Why the one you incorporate a regressor as a expansion variable will be complicated. And you know what? In that case, we are going to use a likelihood ratio test. Don't forget, we also use likelihood ratio test when you are comparing between nested variable, either in logistic or in the Poisson regression model or in beta regression model, because the three of them, they actually belong to a generalized family model. Okay, now pay attention. When you write that, the result is going to be this. You know what it's telling you is that your model one is a conventional beta regression. You are not considering any explanatory variable as a expansion variable. But what about the second model? Which of them? You consider temperature as a expansion variable. Oh my God, at the end of the day, look at the p-value associated with your comparison. Do you know that in your non-hypothesis will support a simple model? The alternative is going to support the complicated model. The complicated model here is the model that are, where that contain the expansion variable. Now, is there any question here? So which model is good now? It's better now. Oh, go ahead. Which is model two? Okay, kind of. What you just said now, are we verifying whether temperature is has a significant contribution, making the model less linear, right? Yes, less linear. Something is not going to be non-linear. It's not going to be not a linear if there's a violation. And violation exists here because there's always going to be a violation when you are considering response variable in the range of 0 to 1. Does that make sense? Always there could be violation when you are considering response variable in the range of 0 to 1. Does that make sense? Now, when there's a violation, what kind of violation are we talking about? Oh my God, the one with the Poisson regression model that we did yesterday, the violation was normality. But the one we're doing now, the beta regression, the violation is both normality and the constant variance violation, which we call the heteroscedasticity. Now, what we're trying to do here, if you look at model one, in model one, we are looking at the effect of batch and temperature on the yield. But model two, in addition to look at the effect of batch and temperature on the yield, we also want to see which of the explanatory variable can be found culpable in the violation. Does that make sense now? That rings bell, right? That makes sense, right? Okay, now what this guy is now telling us, because this is performing a nested test now of comparison, and the p-value that we have actually suggests that we are rejecting, because the p-value 0.037 is less than 0.05, we're going to reject the simple model. Then that was why I said no, that this can also be interpreted as testing the non-hypothesis of equal expansion against. Now I needed to take a look at this. Equal expansion. What does it mean? Equal variance. You know what model one is saying? Model one is saying, leave explanatory variable alone. There's no problem anymore. The beta regression has settled the problem. But the model two is saying, no, the conventional did not solve the problem unless we arrest somebody who is responsible for the violation so that it doesn't cause the problem again. That is what it's saying. So the non-hypothesis is going to say equal expansion. The alternative is going to say unequal expansion. Does that make sense? Unequal expansion is heteroscedasticity. Does that make sense? Okay, now I'm going to go into another example now in economies, house food expenditures. I told you the other time, it's not, you don't spend all your income on food, right? You got other things that will spend money going on. Now, the house food expenditure data for 38 household, the dependent variable is food divided by income. Of course, food that you spend on it. Okay. Now, the proportion of household income spent on food, and they identify two explanatory variables. Like, for instance, what are the variables that could affect the amount that I spend on food? Now, previously mentioned household income and the number of persons living in the household. How are we able to get this? Maybe we approach those in economies and they give us this. Now, you know what we want to do? What I for us want to do here is, what this test is talking about. This is what we call a Brechberger test, a test on heteroscedasticity to see whether there's a violation on the data. Okay. And of course, the p-value here is very close to core, 0.005. That's too close to core. That may be a problem. Now, what I want to first do, okay, we consider a linear regression model fitted by, if you consider a linear regression model, okay, what we're trying to world, that's not going to be okay. Okay, but take a look at if you take a look at what I have here. What am I trying to say? Fit a linear regression, right? Can you see LM? You see LM, right? That's a linear regression, right? Okay, I just want to show you something. It's not appropriate for this. Why? Because this guy is a proportion. Food, amount of food divided by income. You don't spend everything, it's going to be in the 0, 1. Okay, I just want to fit that for you to see. Okay, and when I fit that, I also fit, this is the one for beta regression. But in this one, have I included the expansion variable? Somebody should look at the code. Have I included the expansion variable? No, there's no expansion variable. This is just a conventional beta regression model. Take a look at that. Okay. Now, this is the result that I got for the beta regression model. Okay. Income and persons. Can you see that, right? Now, take a look at this. If you also, okay, maybe I didn't run this. If you run this guy, it's going to give you the one for linear regression, but that is not appropriate. It's not appropriate. But you know how you're going to know it's not appropriate? You can carry out the regression diagnostics. There's going to be a lot of violations. Does that make sense? Okay. Now, take a look at this guy here. Here, this is fitting the conventional beta regression, right? Believing that we have equal expansion, right? Believing that the shape parameters in the beta distribution has taken care of the violation. Oh my God. Can somebody tell me this model, have I considered the expansion variable? Yes. What is the expansion variable that I'm considering? Persons. Can we reason now? Oh, what determine most? What could make the amount I spend on food to be changing like that? For the variance to be changing like that, should be the number of persons in my household. Number of persons in my household. But you know what? We can do this. We can try possibility. Okay, let's say I didn't get any information from anybody. You know what I'm going to do? I will fit to one more model. Here, what did I do? I use persons as a expansion variable. In another model, I'm going to use income. Does that make sense? Then I'm going to compare them. We we live in a world of comparison. Why can't you try possibility to be able to know the one that work at the end of the day? Okay, now in the end here, what is the first model? The conventional beta regression that assume equal expansion. The second model, I put persons. What happened? Significant, which means the second model is better. Okay, and let me take a look at this. Do you know that you want to, let's say you want to compare three models at a time? You know the one I've been giving you, you'll be comparing two, right? What if you want to compare like three models at a time? What are you going to do? Oh my God. You're going to use AIC. You know what you're going to do? AIC, you can write, you can list all the models. Here, I'm only listing two. Even if you have 10 models, it's just going to be, take a look at this guy. Maybe this one is for the first one. This is for the second one. I can continue to list as many as possible. Model. Do you know the best model at the end of the day? The one with the lowest AIC. You remember the other time we did criteria for model fitness and model complexity? AIC. Now, which one has the smallest AIC here? Is the second model, -80. And what is the second model? That agree with their test here that choose the second model. You can list as possible as many variables. Doesn't matter. I mean many models, and then you choose the best among them. Okay. Now I'm going to another thing now. Do you know in beta regression model, we also have an advanced transformation based on the link function. You know, the level of intervention at time depends on the magnitude of the problem. Do you know the link function I've been using before now? I've been using just the uh ordinary one. Okay, but take a look at this. I need you to take a look at this guy and this guy. What is happening? Here, I introduce a new link function that is log. But if that guy can solve my problem, I don't need to come here. I'm sorry to use this example. Has anybody know mosquito? Mosquito, right? We used to see it a lot in Africa. And I want to kill mosquito and I take a gun to kill mosquito. That's not economical. So if something lesser can do the job, why do I go? Why do I waste resources? But at times, we may need, in research in general, there's no crime in exploring possibility. Now, yeah, I introduce a log, okay? And when you introduce a log, we also have a way to see if we have improved on the model. You can do the AIC that I said the other time. You can do the likelihood ratio test, or you look at the pseudo R-squared. Now, this one is a conventional one, even without introducing a expansion variable. But there, I did specify the link, right? That's if where I don't specify the link, I'm just talking about the conventional, the base one. But here, if I introduce the link, look at the R-squared, the pseudo R-squared. This actually is better. Okay, that link function is better. But at times, this is maybe enough for us. 96, okay. Why am I, So it depends on. Now take a look at this. I told you the other time. Take a look at the first module. This is a conventional module, right? Without even introducing variable expansion. What is the second one? I introduce variable expansion. And the conventional, but I just use a log as a link function. Do you know that those are three different models, right? I may want to know which one is better. Should I use the conventional beta regression model, or I use the one where I introduce a expansion parameter temperature, or I did not even introduce the expansion parameter, but I just change the link function? Then I'm going to do the AIC. After running that, you see that? You see that this is it. You see this guy here, this guy here, this guy here. Then I'm just going to write the AIC of all of that. I'll choose a model with the lowest AIC. Which one is the lowest? Point to the log. Go ahead. And that is why we need to explore possibility. I don't know which one is going to work for a future data until I try this possibility. And I'm going to tell the world. When you say this is my best model, they're going to, if you want to listen to, you know why I like science, why I like research community in general, there is nothing like authoritarianism, where you're going to say, oh, this is this, and you can't prove it. No, they're going to tell you, which criteria are you using? You say, oh, I'm using AIC. AIC is an household name criteria to be used when it comes to model selection. Now, for this data now, it's trying to tell me I should go for this. For another data, I may not be able to say until I try possibilities. Oh my God, this is going to be the end of beta regression model. Now, what am I trying to tell you? When you read some articles in the past, do you know that some of them, when they are working with rates, proportion, they've been using logistic regression? That's wrong. When you use a wrong model, you're going to mislead the people. We don't want to, it's not as if our models are failing us, but we are the one that we're not doing the right thing. We need to be guided. In statistics, we got a lot of models. All what you need to do, spend your time, identify a statistical model that is appropriate for a given situation. But do you know whenever you are, or whenever you are trying to look at a relationship analysis, the most important thing in relationship analysis is to put into consideration the nature of your response variable. The nature of the response variable determines the regression type to use. Tomorrow now, we're going to go into another story. We're going to talk about multinomial logistic regression. That's another variant of logistic regression. And we're also going to talk about ordinal logistic. That's another variant. And that is the reason why then, when during the pandemic, it looked as if the health officials are confusing the world, where they're going to say, oh, there is this COVID is different from this COVID. They call one Omicron, they call one the better version, that version. You know what? You may not be able to treat this version with what you are supposed to use for another version. We got variants of logistic, just like the same way we have the variants of COVID. So where to use a Poisson regression is different from where when to use the beta regression. But the bottom line is understand, get yourself familiar with the nature of the response variable. Is there a question before I go today? Go ahead. How do we work? How are we going to know if it is beta regression model? Or you mean integrate that? Oh, interpret. Oh, okay, that makes sense. That makes sense. They come the same way that we normally interpret. For instance, now, let me just, that's a good question. Coming here, the question now is, how do I interpret this guy? Right? Okay. Now, in the case of beta regression model, okay, we did not talk about the log or something or the logod or whatever. You're actually going to interpret it the same way you interpret the linear regression model. You know why? Linear regression model, response variable is continuous, but it's not bounded between 0 and 1. But in the case of beta regression, the response variable is also continuous, but it is bounded in the 0, 1. So it's the same interpretation. Does that make sense? Why the same interpretation? They are both continuous. One is bounded, the other one is unbounded. Except that you will be mentioning rates, depending on whether you are working with poverty rates. For instance, now for a unit increase in income, what happened? It's actually going to lead to what? A decrease on average, a decrease in the what? In the gasoline rates. You can't just say in the amount of gasoline. No, rates. You have to mention that rates or poverty rates. Oh, that guy. I think you've asked a very good question. You know what I need to do? Send me a message for extra credit. I love that question because when you fit a model where you've done everything you're supposed to do statistically, how do we present it to the general public? And that is where interpretation comes in. Okay, make sure you all stay safe. I'm going to see you tomorrow. On Friday, my TA is going to walk you through midterm 2 practice question. I've already uploaded it. You've first seen it, right? Okay, that is the pattern that I'm going to go over. In fact, you know what? Your exam, the midterm 2, you can open anything. Does that make sense? You can open, but the only thing you cannot do is you cannot seek assistance from anyone. You cannot provide assistance from anyone. And when you need to join Zoom, just like the way we did the other time, we want to see your video. We want to see somebody who's behind the scene. Go ahead. Yeah, it's gonna be over this weekend. I think it's starting 12 on Friday. So it's gonna be there for 48 hours until Sunday. I think what I'm gonna do is I'm gonna push it down up again to when it starts 12. Because to me, 12 to 12 noon on Sunday is 48 hours. I put 48 hours in the announcement. I think I'm going to change it from, I'm going to say 12 on Friday, 12 noon on Friday to 11:59 p.m. on Sunday. That's going to be a lot, right? Yeah. But when you are not ready to start, don't start. It has been programmed. And before you start, if I were you, you know what you're going to do? Open your materials ready before you go and click on. Open your textbook, open your notebook, open whatever. Do whatever that will make you to succeed in that exam. But the only thing you cannot do, you cannot communicate with your friend. You cannot seek for assistance. You cannot provide assistance. But make yourself comfortable. Do whatever that will make you to pass. Make sure you all stay safe and have a lovely day. Bye for now, everyone. And you too. Oh,
Thank you.
okay. I got that. I got that.